Hello friends, in this lecture I am going to discuss about some numerical problems, and after solving them I will try to give you an idea how the properties of ROC can be applied and how the integral formula of Laplace transform, which I discussed in the previous lectures, how that can be applied to solve some problems. So let's get on with it. Let us start the first problem. Find the Laplace transform of the function xt equal to minus u of minus t, where u of minus t is a mirrored version of unit step function. So in order to solve this problem, let us first define how u of minus t looks like. This can be mathematically defined as u of minus t, it is equal to 0 when t is greater than 0 and it is 1 when t is less than 0. Now, according to the definition of Laplace transform, we can write that Laplace of any function xt, which can be written as x of s, and that will be equal to integration minus infinity to plus infinity xt into e to the power minus st dt. Okay, let us name it equation 1. Now the definition of u of minus t is to be applied into equation 1, and after the application of it we will be having the following equation, that Laplace of xt in this case will be minus integration minus infinity to 0 minus integration minus infinity to 0 1 into e to the power minus st dt. Now this can be solved by normal integration, and after we find the integration we are going to obtain the following result: 1 by s into e to the power minus st, where the limits are from minus infinity to 0. So after we substitute the limits, the following can be obtained, that it will be 1 by s into e to the power minus s into 0 minus e to the power minus s into minus infinity. So eventually it will become 1 by s into e to the power 0 into e to the power s infinity. Let us call it equation 2. Now for the Laplace transform of xt, that is xs, to exist, x of s must be finite, and from equation 2 we can conclude that x of s can be finite only if s less than 0. Got it? So under this condition xs will be finite. In that case x of s will become (1 by s into e to the power 0 into e to the power minus e to the power minus infinity. So essentially it will become 1 by s. And from the condition when x of s equal to finite, we can get the ROC. So the associated region of convergence or ROC will be real of s less than 0. So in short, Laplace transform of the function minus of u minus t, that is 1 by s, along with the ROC real of s less than 0. Similarly, now let's take another example. This time the function xt is e to the power at into u of t, where a is greater than 0. We know that ut is the unit step function, which can be defined as ut equal to 1 when t is greater than 0 and it is equal to 0 when t is less than 0. Therefore, from the definition of Laplace transform, x of s will become integration minus infinity to plus infinity xt into e to the power minus st dt. Now putting the value of xt in this equation and utilizing the property of ut, eventually we will get an integration 0 to infinity e to the power minus at e to the power minus st dt. Now this integral can be rewritten in the following way, that x is equal to integration 0 to infinity e to the power minus of s plus a into t dt. So by applying the properties of integration, it can become minus 1 by s plus a into e to the power minus s plus a into t with the limits t equal to 0 to t equal to infinity. So after putting the values of the limit, the value of the Laplace transform becomes 1 by s plus a. So we can conclude that Laplace transform of the function e to the power at ut will be 1 by s plus a. How about the ROC? As discussed before, at the ROC the function is finite. Xs will become finite. So let us find out the condition when xs will be infinite. And in order to do so, let us take the denominator s plus a. Clearly, when this denominator s plus a equal to 0, this will give to the condition when x of s is not finite. So the region of convergence in this case can be written as real of s greater than minus a. Because again I repeat, when s will be equal to minus a, then the function becomes undefined, that is, it is not finite. So the ROC will be real of s greater than minus a. And in connection to the properties of ROC that we discussed in the previous lecture, I would like to reiterate the fact that there was a property that for every right-sided function, the ROC is outside of a pole. That means real of s greater than sigma max. See, in example 2, it is a right-sided function xt, and we obtain the ROC in the form real of s greater than sigma max. So it is a verification to the fact that the properties are actually true. On the other hand, if we go to example 1, xt is a left-sided function. Look at the expression of ROC. It is of the form real of s less than sigma max. In this way, this integration property or the basic definition of Laplace transform can be applied to find out the Laplace transforms of any functions. But in the later section, we will learn various properties of Laplace transform which, if applied properly, can save time and integration, so that for simpler problems, simply by observing and applying correct properties, one can find out what will be the Laplace transform along with the ROC. So if you like this video, please subscribe to my channel and press the bell icon so that you get notification whenever new video is being uploaded.